So hello everybody, my name is Alceste. I'm a lecturer at Aston University. As you can guess from the first slide, this is an academic work, and this is the first time I present it outside, let's say, academic conferences, and I'm really keen on hearing your feedback, and also I'm really grateful to John Pretty and all the organizers to having invited me. So this work is about verified message passing programs in Dotty with a toolkit that is called Effpi. And the kind of problem this work addresses is the fact that now, as you, I guess, know very well, the programming distributed and concurrent applications using message passing is, let's say, very mainstream. If you use akka, that's basically what you do. You have actors exchanging messages, but there are many other tools and languages like Go or Erlang that do similar things. The issue is that, however, this approach is very intuitive, but does not allow to formally verify whether an application is implementing a desired behavioral specification. And many errors, like protocol violations and deadlocks, are only found at runtime, so when they are harder to fix. So the idea of this work and this toolkit called Effpi is to allow for a form of strongly typed concurrent programming using Dotty that has very nice features for that. And there is an underlying theory that uses types as behavioral specifications and uses model checking to verify program properties. So it may sound a bit vague at the moment, so I will try to convey the idea with an example that is actually adapted from a use case for akka typed. So let's say that you need to implement a payment service that is supposed to listen for payment messages forever. And every time a payment request arrives, the service should either reject by answering a rejection message or report the payment to some auditing service and then accepting the payment. And then the protocol loops. So if you implement this thing in Effpi, you can write this code that I guess looks familiar, especially if you know akka typed, because what you have here, you have this payment actor, if you can see my mouse, that has a reference to this auditing service that is an actor reference. And this is an actor processing messages of type pay. And every time a new message pay arrives, then it's checking the amount of the payment, and then it's either answering reject to the sender on the reply to field, or it's sending the payment to an auditing service and then accepting the payment by replying to the sender. So this is exactly the implementation of the specification, but there is nothing that really constrains this to be correct. Actually, if you, for instance, let's say, forget to audit the payment, of course, the compiler is still happy. By the way, this is Visual Studio running Dotty and without any change. So this still type checks. However, with Effpi, what you can do is you can add this type annotation. Here. And now suddenly the Dotty compiler is complaining. It's saying, wait, this is wrong. And to fix it, you have to restore the auditing. And actually, if you look at this error that the compiler was reporting, if you clean it up by removing some namespaces, the error that the Dotty compiler was reporting was, wait, I found an output of accepted to an actor reference, but what I wanted to see here was either a rejected message, or, this is a union type from the previous talk, an auditing followed by an accepted message. So that the compiler is telling you that it understands the protocol it should have seen, and now it's not happy. And the trick I did earlier was that by adding this type annotation here, basically I am telling that this actor should behave according to this type that is defined earlier, called payment, that formally defines the payment protocol that I wrote in English in the previous slide. So it's saying that I should loop forever and read a message and either reject it or, union type, send an auditing and then send accepted. So in the rest of this talk, I will try to explain how this works. So by giving some background and then an explanation of how Effpi is implemented. So I will start with the background. I will go quite far in the sense that, as you all know, the lambda calculus is like a canonical model for sequential computation, and you, I guess, all know that it is at the basis of functional programming. Everything started almost 1 century ago, basically, in the 20s, 1920s. And then the lambda calculus was like the theoretical playground where many ideas were experimented with, and then they ended up in programming languages like type systems or parametric polymorphism, that is generics. So this is for sequential computation, but for concurrent computation, there is also a canonical model that is not as old and not as known, but this is called the realm of process calculi that basically formalize concurrent and distributed systems. And the history here starts around the 70s with Robin Milner, and then also Tony Hoare was involved in a similar line of research. There has been lots of development, but as you can see, this is more recent. And the blue highlights here are two calculi that are called CCS and the pi calculus that I will be basically using as background in the next slides, even if I will not go into the details. So what's at the core of this formalism? Well, the idea is modeling processes like P1 and P2 here that interact via communication channels, like C here, and with a formalism that allows to reason on behaviors and correctness of behaviors. So for instance, in a process calculus, I could write something like this. This is a process that is using a channel C to send a message 42, and then is using C to receive some answer X. I can compose this in parallel, which is this symbol here, with another process that is now using the same channel C to receive some Y, and then it's sending, again, over channel C, Y plus 1. So the calculus has rules to, let's say, to reduce these expressions, like more or less like mathematical expressions. So what happens here is that we have a send and a receive on the same channel. So this configuration reduces by interacting to what follows the first input and output. So now we have the first process is trying, after having sent the message, to receive. The other one has just received 42 over Y. So Y is now replaced with 42. So it is now trying to send back 41 plus 2. And this reduces to the configuration where both processes have terminated. They are all happy. So we can consider this a successful, a correct interaction. You can also write things that don't behave as nicely. For instance, if you write this process, these two processes, one is trying to send hello and then receive a reply on channel C. The other is trying to receive Y and then send back Y plus 1. As you can imagine, these two interact. So now hello replaces Y, and the result is that this process is trying to send back hello plus 1. This is not what you want. So in this case, the calculus is modeling an incorrect interaction. Or you can have other errors, like, for instance, two processes. One is sending 42, waiting for a reply. The other is expecting a message and then doing nothing else. They talk, they interact. So this one receives the message. It has terminated. The other remains waiting for a message that will never arrive. So this is also arguably incorrect. So this model allows to reason and formalize all these situations that you can also find in, let's say, real-life applications. And the kind of use you can make of this theory is mainly on two main applications. One is model checking. So model checkers are tools that essentially allow you to provide the specification of a system using process calculi or other formalism, and then they will generate internally all the possible executions and reductions of the system, and they are able to verify whether the system will always behave as intended, or if it will ever reach a state that is not wanted. So you can basically look for good events, see whether good event will always eventually happen, for instance, or bad events will never happen. These properties are called safety and liveness. And the goal is to find bugs and prove correctness of systems. And one of these tools is called MCRL2. We'll be using it later. And you can find in its website several use cases like finding bugs in the control system of the CERN's Large Hadron Collider. So the tool was used to spot some problems in the system and fix them. So this is one use of process calculi. The other is more or less like the lambda calculus, to use them as programming languages, and then also introduce types. For instance, types for channels. So, for instance, let's say that we have these two processes that from the previous slide. One is sending 42, the other is waiting for an answer. It's sending 42 and then waiting for an answer. The other process is expecting y and then sending back y plus 1. We can give a type to the channel C with this kind of formalism. It is saying, OK, C is a channel that is used to transmit integers. And since C is used in the same way on both sides, by both processes, this is type safe. And this kind of channels with types may remind you of ACA-typed, where actor references have types. And with types, you can also spot that, for instance, these two processes, where one is sending hello and the other is receiving and sending y plus 1, are not right, because the type of C, of the channel, on one side is used to transmit strings, on the other side is used to transmit integers. So they don't match. So this is incorrect, and indeed, this allows to rule out the incorrect behavior. Still, it is not quite enough to have all the guarantees we may want, because, for instance, consider this other process from the previous slide, where one is sending 42 and waiting for an answer. The other process is waiting to receive y and then doing nothing. They are both using the channel to transmit integers, but as we have seen, they will deadlock, because after the first interaction, one will terminate, the other will keep waiting for a message. So channel types are not enough to avoid these kind of problems. So to address them, we need more. We need more advanced types that are called behavioral types. So we need to add this further information here when typing processes. And now this type that looks a bit weird, it's telling us that C is used first to send an integer, then to receive an integer by one process, and the other process is just receiving an integer. And now the types basically represent protocols with sequences of interactions, and the checking types amounts to checking whether a program is implementing some protocol. That's the key idea here. And notice that now types are like kind of mini processes themselves. So this means that we can use model checkers to check the types and see whether they have some desired properties. So in this case, we can spot that this system will reach a configuration where one process is waiting for a message that will never arrive. So it's wrong. But the problem is that now things are becoming quite fancy and really not the kind of types and things that you expect to see in a, let's say, mainstream programming language. So if you want to implement this now, you start needing to implement a new language, a new type system, which may not be, let's say, very successful, probably. It's very hard to now propose something for practical use on this direction. So what happened in the recent years was that there was some work in several programming languages to bring these kind of behavioral types into the language without changing the language at all, or not so much. And for Scala in particular, I worked on this by developing a toolkit called L-channels that has a mainly academic background, so I was very worried to make it connected to the theory of behavioral types in a variant called the session types. But then I was not able to obtain very strong compile time checks by the compiler. So there are some guarantees, but not all those that were, let's say, desired and in theory provided by the formalism. But at the same time, there was Roland Kuhn, that I guess you know very well, that managed to do an alternative implementation of the same theory called ACA-typed session. It's available on GitHub, that has quite interesting compile time checks, but for me at least was a bit puzzling because it did not really look like the theory I was familiar with. So it took me quite a bit of time to understand what was different fundamentally with the idea of basically come up with a different approach. And now, after some work, I and my co-authors managed to obtain this result, this toolkit called Effpi, that has both let's say, a strong connection to theory, even if the theory is not the same. Actually, we had to develop something new, and also provide pretty strong compile time checks. And now, in the rest of this talk, I will provide some details about Effpi. But before I continue, is it clear so far? Is there anything confusing? OK. I cannot see whether anybody is raising their hand, so please shout if I'm missing you. OK. So Effpi is, first of all, a domain-specific language to write concurrent and distributed applications. So the idea is to provide primitives to send and receive messages. That's the gist of it. So in this example, I'm using the Effpi DSL to implement a ping-pong system. I have a pinger process here that is taking two channels. Self is a channel that basically it's its own identity channel that it's going to use to receive messages, and it has a channel that points to a Pong process. And this pinger process is sending its own identity on the Pong channel with this send operation here. Oops, sorry. And then it's waiting to receive a reply, and then it prints that it received the reply and terminates. The Ponger process, instead, only knows its own identity. So this is a channel that carries strings. So what's going to happen here is that it will use this self channel to receive another channel, a reply to channel, and use it to send back hello. You can find this kind of pattern in Akatyped, where it's usual that an actor sends its own actor reference to another actor to get back a reply. And what you can do is you can create channels here, C1 and C2. You can spawn Ponger and Pinger in parallel by connecting them with the channels you just created. And then, since the DSL is not doing anything, it does not have side effects, but it's returning objects that describe the intended behavior, you can evaluate what has been constructed here by par, Pinger, and Ponger, and the Effpi runtime will run it for real. And this will cause the processes to be spawned, and they will communicate. And behind this DSL, there is actually a kind of lambda calculus with communication and concurrency. I will not give the details. Also, this is pretty well hidden by the Dotty syntactic sugar, but this is what allows us to basically connect to the theory. The theory is actually called the higher order pi calculus. I will not go into details. But the key here is that there are lots of lambda terms in these two code snippets that model abstract processes and continuations after each input-output action. So how can you type this DSL? Well, what you can do, as I said, is you can give types to channels, but they don't disallow deadlocks and other errors like protocol violations. So what you can do instead is you can use these types provided by Effpi. For instance, this type out is, let's say, the type that describes the effect of sending, in this case, a string over a channel that carries strings. Then you can compose this type, like here I'm composing two outputs. And then you can use these types, these are the behavior specifications, to annotate implementations, like in this case, a function f, and check that actually what the function is doing, in this case, sending two messages, matches the type. If the Dotty compiler sees that these two send actions match the two outputs in this type, then it's going to type check and compile. So this is the key trick. But at this point, this is not yet enough to have, let's say, precise behavior specification. And the issue is that the type of this function here, that is just saying output a string on a channel, is not saying which channel is being used. And this is a problem, because if you have, let's say, a complex system with multiple channels, there is nothing in the type that suggests what exactly the code is doing, and you cannot really reason about it. I mean, this F may even just create a channel and send something in it without ever using C. So to sidetrack this problem, what you can do is infuse this kind of behavioral types with Dotty's dependent function types. This is one of the main new features of Dotty, the fact that you can define basically functions where the return type, like in this example, depends on the name and the type of the argument. So here I'm defining fun of x, that is an integer, as a function that returns a list of x-type elements. And the only way I can build such a list is to build a list of x's. This is guaranteed that the list that I return will not contain anything but x's. And if you infuse this idea into the behavioral types provided by Effpi, then what you can do is, for instance, you can define this type t with a parameter that is a channel type that is expected to output a string on the parameter. Then you can, for instance, compose this into t2 that is taking two parameters that are both channels and is sending a string on the first channel and then on the second. And then you can use t2 to type annotate the code you write with the DSL of Effpi to make sure that the implementation is actually following the protocol that you have defined in the type. So for instance, here, if you define f taking a string and two channels, C1 and C2, if you put this annotation that says, I want this to behave as type T2, but with the parameters instantiated as C1.type and C2.type. This means that when these parameters get threaded inside the type, then it's guaranteed that the first output will be using C1, the second output will be using C2. If you try to, for instance, use C1 twice, it will not work. You will get a compile time error. And this is really the key to have, if you want, you can have enough type information about the communication occurring in the process to be able to reason about it. So the Effpi DSL offers several types that allow to formally define as a type the intended protocol that a program should implement. And then it has corresponding operations in the DSL that will allow you to build objects of those types that represent the actual interaction. So for instance, you have the type that represents, let's say, the effect of outputting something of type T on a channel C. And to realize this effect, you have the operation send, for instance. You have an input type that represents the behavior of using channel C to input a variable of type B and then continue as a lambda term, as a closure that takes the value that has been just received, that is of type B, and then behaves as P. P is the behavior that will follow the input. And to implement this kind of type, you can use primitive operations like receive or read. Then there is the sequencing. Once you have two behaviors, you can implement one after the other by chaining them with this type level operator that actually has an operation that is the sequencing. You can implement protocols with a choice. For instance, at some point in the protocol, you may be allowed to either send something to some actor or send something else to some other actor. This is very straightforward in Dotty because there is the union type. So what you can do is just say, OK, just define the two intended protocols that you can choose from and use the union type as an alternative. And then you can choose what to do by using if then else or pattern matching or just doing one of them. And this is very, very nice. Also, there is a parallel type that essentially is saying this protocol P1 should be executed in parallel with P2. And to instantiate it, you can use operations like par or fork or spawn. The effect is kind of the same depending on the context. One may be more handy than the other. And then there is recursion. That is a kind of a hack because Dotty does not support recursive type aliases. So there is this kludge where we have this recursive type that represents a loop that actually loops when you stumble into a loop operation. And you can implement it by writing a rec block that at some point loops or using forever. That does kind of the same but with less noise. So after this, I will go into let's say a slightly larger example. But before continuing, I'd like to know if it's clear enough, if you have questions. No? Question?
What are the parameters of in? There is a channel. And
so intuitively, what you would just need is just a channel that is going to be used, and then a function that is what will happen after you get an input. So the input will be threaded, so given to the continuation, and it will be used there. So, but the thing is, you need to define that B is also the parameter, so there is this B that is repeated. So B is the type of the input that is going to be read from the channel. So there is some redundancy here, but it's due to some. I will show an example shortly. But okay, I think there are no more questions. So okay. So now to show what you can do and what you cannot yet achieve with what I've shown, I will go into the classic academic example of the dining philosophers that probably most of you already know about. So the problem here is you have a set of programs or philosophers that run concurrently, and each program is supposed to acquire two shared resources that are the forks, perform some task after the resources have been acquired, that is eat spaghetti, and then release the resources by dropping the forks, essentially. And the problem here is, one, make sure that really each program here is following the intended protocol, and also that the whole system will not deadlock. So in Effpi, or in any process calculus, what you can do is model the whole problem as a set of processes. So the philosophers are processes. The forks that are going to be acquired and released are also processes. And they all exchange messages using some channels. In particular, what you can do is use one channel to signal where you are acquiring a resource, so a fork, and one channel to signal when you are releasing it. So the blue channels are for acquiring, the red ones are for releasing. And of course, there is competition because two philosophers may want to try to acquire the same fork at the same time. So what you can do is you can write code like this to implement a philosopher. So it's taking its own name, and then 4 channels, basically that allow to pick and drop 2 forks, and they are going to use those channels in some way. In this case, this philosopher is using the first channel to pick a fork, then the second channel to pick the other fork, and then it's dropping both forks and then looping. And then you can instantiate many philosophers in parallel, like in this case, and several forks by just basically passing them several channels that they should use to exchange messages to each other. This is, again, more of the Effpi DSL. In particular, notice here that in receive, we are using a channel to receive the fork, and then here we can use what we received. But, we refer to the previous question. So, okay, we can write this. Of course, we would like to know whether it's correct, whether it's using the forks as intended, so whether the resources are being accessed in the intended order. What you can do to make sure that it is the case is write the type first. You can write the type of a philosopher that is the intended behavior of the philosopher. In this case, the type is taking the four arguments that are all the forks that it is supposed to use. And the type is saying, okay, you should loop forever, and you should pick the first fork first, and then use pick 2, and then output drop on the first drop channel, and then on the second drop channel, and then loop. So with this type here, if you add this type annotation to your philosopher implementation, the Dotty compiler will tell you whether the implementation is following the protocol or not. And I can show you quickly in Dotty. There is a larger implementation of the problem, where here I have, I think, it's the same. So I have the 4 channels. I have this annotation that is telling me you must use these channels according to the philo protocol. Well, I have this code, it's type checking. What if I try, for instance, to use the wrong channel here? The Dotty compiler says, no, this is not what's expected. The message may be a bit noisy. You need to clean up all the namespaces. Unfortunately, that's not much I can do about that. But here the problem is the type is reflecting the fact that I'm not using drop 2 at this stage of the implementation, but drop 1. So I'm using the wrong channel to interact with the rest of the system. And this may cause problems, of course. So the compiler is only happy if I use drop 2 here. So, okay. We have now the guarantee that the philosopher is using its channels in the order and expected by the protocol. So I guess we can run the code. So I will run the Dotty Philosophers, and it will get stuck after a few interactions. So what's happening here is that the whole system deadlocked. And maybe if you're familiar with the problem, you may already know what's the issue here. Is that in this very vague, let's say, specification of the system, I'm letting all philosophers acquire the resources in the same order, and in particular, they may get stuck after a while if they all try to acquire the left fork first, and they acquire it, because then none of them will be able to acquire the right fork. So how can we fix this? If you remember or know the solution, actually there are many solutions. If you have suggestions. Pardon? So like a timeout, basically having a timeout where if a philosopher cannot acquire the second fork, it will release the first. Is it the suggestion? Yes. Yeah, that's a solution, yes. There are others. Okay, I will tell you one that I found on Google. The solution is, it's enough if you just let one philosopher acquire the forks in the opposite order. So all philosophers acquire the left fork first and then the right. If you just let one of them do the opposite, this is enough to avoid deadlocks. So, is it true? But also, assuming that this is true, how can I be sure that actually I'm implementing it correctly? Well, this is what, let's say, the next stage of Effpi, in the sense that what the type system and its types, its behavioral types allow to do is to make sure that processes are type safe and that they conform to some desired behavioral specification. However, the language of the behavior specifications that is supported by Effpi is quite powerful. And actually, it's powerful enough that you can implement complicated systems. You can have emerging behaviors when you compose the types that you may not be able to see immediately. And you can model deadlocks. So in this case, what I just did with the Dotty philosopher problem is implement a complicated type that deadlocks. And it's not easy to spot it, let's say, by just looking at it sometimes. So this is why Effpi implements a further verification layer that uses model checking at the type level. So the idea is the following. When you write Effpi code, you can add this kind of annotations, like Effpi verify, where you are asking, please check whether this type specification that can be very complicated, maybe composing many types and behaviors, check whether this type here, this behavior, has some high-level property that I want to be true. For instance, deadlock-free in the case of the Dotty philosophers. Or there are other properties, like reactive means the process will always eventually process the inputs that it is being given. Or there are others that are discussed in a paper that we published. They are mainly, we chose them because they allowed us to write some interesting examples, but the list of properties can be extended. So you write this kind of annotation, then what happens is that we wrote a compiler plugin for Dotty that does some internal machinery. Basically, it converts this behavioral type written with our Effpi types into an internal format that is based on the underlying theory, and then takes this property expressed as a mu calculus formula, and basically feeds everything to a model checker, and asks the model checker, please check whether, for instance, the type of the Dotty philosophers is deadlock-free. And the model checker will say yes or no. So in practice, this means that if I go to my Dotty philosophers implementation, I can go, for instance, here. So this is the type, the part of the code where I'm composing 3 philosophers and 3 forks. And there is a type that says how they are supposed to be connected. So now this is compiling, but if I uncomment this annotation here, now the compiler plugin is feeding this behavioral specification to the model checker, and the model checker is returning an error that is also returned by the compiler plugin. And so this squiggly yellow warning here is saying the property does not hold. So this means that it is not the case that this protocol here is deadlock-free. However, so there is another implementation of this, another specification of this problem. So instead of having this dining type here that connects the forks and philosophers in the order that I've shown that doesn't work, that deadlocks, there is another type called dining df that has only one difference. It is now swapping the order of the forks of only the first philosopher. And here, if I change the type annotation, the Dotty compiler is complaining because the first term is not matching what's expected. Again, the error is a bit noisy. But the issue here is that dining df, that is deadlock-free, expects Socrates to receive first this channel and then this other channel. And now it compiles. And now I have no warnings in Visual Studio. So it means it is true that this behavior here is deadlock-free. And also it is true that this implementation I have here follows this specification, because the Dotty compiler is checking it for me. So if I try to run this again now, what will happen is that the philosophers will not deadlock. They will start using the resources and releasing them in the correct order, and this will keep running. And to achieve this, again, you need both layers. You need a type level layer where you check the conformance of code and protocols, and a verification layer where you check that the protocols have high level properties that are somehow inherited by your code. So, is it clear enough? Any question? Yes?
Are these properties always decidable?
So that's a very good question. So not always, in the sense that you need to have basically a type, a behavioral representation of the intended protocols that is not Turing complete for sure, but also it depends on the logic. So in this specific case, what's happening is that the types we are using are not too expressive. So basically, all properties written in the linear time mu calculus are decidable. And the linear time mu calculus is enough to represent the properties I have listed. So for these examples, we are within the decidability boundary, let's say, and there is much more you can write. But in general, what may happen is that you may use let's say, a language for behaviors that is too rich, and then maybe the logic you want to use for model checking may become undecidable. So it's not generally possible. You need to strike a balance here. There is some subtle, let's say, choices to make. In this case, we choose a protocol language that is decidable with a pretty rich logic, and this is so it works for these cases. Okay.
I have a question.
Yes.
What if using the resource by a given philosopher takes different amount of time? So philosopher A may take some time to use the resource, and the other philosophers may take another time, like random times. Can you check if if the code will still be deadlock free or not?
So I repeat the question. So the question is about essentially whether I can have some timing guarantees. But if, for instance, a philosopher is taking longer than another, whether I can guarantee, for instance, I don't know, in 1 minute, all philosophers will have acquired and released all resources. Is it a good way to put it? Yeah. So this requires a richer formalism that is called timed process algebras, or communicating finite state machines with time, and this is beyond what we did. And it will be a very interesting topic. I'm not sure how to do it, though, also because we need to introduce the values at the type level, so I will need to think about it. But in principle, there is some theory that could be used to go in that direction, but I need to think very hard.
So there is no starvation property, Like one philosopher starves to death because everybody can acquire, but he's always losing, right?
So the question is whether there is any starvation property we can check on this system. I need to think. I think the logic allows to express no starvation. Because essentially what you need to check is something like, it is always the case that you eventually see some input or output on each resource. That's intuitively the kind of property. And I think the logic is powerful enough to express it while still being decidable. I will not swear on it, I need to think, but I think it's possible. It's within this framework. And also there are, again, it may be the case that maybe a more powerful logic supports it, and maybe using a different model checker can check for it, but then maybe you may need to, let's say, have a less expressive behavioral language for the types to be able to decide it. So, but I think that with this logic, with this calculus, I think it's possible to reason on starvation. I think I need to have a look more carefully though. Okay, should I proceed? Okay, last minutes. So, one remark about the beginning of the presentation, where I've shown you an example showing an actor, and then I went on talking about processes, channels, and blah. So, what is the connection there? Well, the idea of this work, of this tool, is that actually actors, or actor-like things that we have, are just processes in disguise. What we are doing is we are using some of Dotty's features to basically do some syntactic sugar on top of processes. In particular, what we are doing is using implicit function types to give basically an implicit context. In this case, an actor is just, so an actor that processes messages of type A and behaves as T is just a process that behaves as T, but when given an actor context of type A. An actor context is just basically a pair of the mailbox that is just, the mailbox that is just an input channel that allows to receive messages of type A, and this is protected so the code cannot access it directly, but it can get it from the context using other operations. And then there is self that is an actor reference. That is just the output side of the channel. So when you send your actor reference around, you are just sending an output channel that can be used by the recipient to send messages to you, and you can read them from your mailbox. That is mailbox. That is just the input side of the same channel. And then you can just basically, when you use this, you use this operation called read, that is essentially accessing the implicit context. So to cut it short, this is what allows to write the opening example, where if you notice, I have this operation read that does not specify which channel is using to read, but what's happening is that it's actually using the mailbox of type pay that is provided by the implicit context that is given because an actor is just a process with an implicit context containing the mailbox and its own identity. So it's essentially it's just a trick. Under the hood, there are just processes. The runtime of Effpi only knows about processes, basically. But it offers, let's say, a more friendly API and more familiar for people that are used to Akatyped, for instance. So other things we did was we implemented a runtime system to run the DSL. And I need to go a bit fast now, but the performance is pretty good. So we compared our performance with Akatyped, and in a bunch of examples, these are just two of them that make us look good. There are others in a paper we published at PLDI. There is some overhead due to the DSL interpretation, but overall, the performance is reasonable and in general comparable with Akatyped, even if, of course, we do much less. Akatyped is a much more powerful framework, but it is at least encouraging and looks viable. And then we benchmarked the verification performance. This table has all kinds of data in it, but the gist is, most of the time in our tests, the verification is basically real time. That's why you could see the warnings in Visual Studio Code in real time when I was checking the data in Philosophers. But there are cases like this benchmark where the verification for a property like deadlock-free terminates in 0.4 seconds, while if you check another property that is called forwarding, that checks whether you are basically forwarding messages from one side, from a process to the other, then it takes, I think, 20 minutes. And predicting how the performance can go may be not trivial. It depends essentially on the size and nature of the formula you are checking. Sometimes even on the number of states, but it's not, the full story is very complicated. But overall, in most cases, it can really run into an IDE. And when it doesn't, you could run it offline anyway. So what about the future? So as I said, I come from academia. We have lots of ideas of things that may be interesting to add on top of Effpi that are interesting, at least theoretically. But what we would really have is some feedback from you. If you have use cases that may look like they may benefit from a tool like this, maybe with some extensions that may allow you to do things that you want to do, then we would really, really love to hear from you. So at the moment, we have some plans. For instance, we have things that are already implemented, even maybe not fully, like the idea of having verified mobile code that you can send around over channels. There is the Actor DSL has several nice, richer operations that are not, however, fully verified, like an ask pattern. So we may want to extend on that direction. There are things we want to do but are not there at all, like, for instance, having value-dependent protocols using Dotty's match types that somebody asked about, but match types are not implemented yet, so that may take some time. We want to give counterexamples when you check a property and the model checker says no. Well, only knows that the answer is no may not be helpful to find where the bug is, but the model checkers do provide counterexamples. So it would be nice to provide them to the user as well. And this is it, basically. So what I've shown you is this toolkit that has an efficient runtime to write strongly typed concurrent programs in Dotty and Scala 3, and allows also for verification using model checking. It is available on GitHub. There are 2 papers about it, one at PLDI, but there is also a short paper at the Scala Symposium that is just an overview. It may be more accessible and less boring. And there is a theory behind it. So if you're curious, you should check the PLDI paper. And what we want to do is, we believe we have some nice basis to do interesting things, but we really need some feedback. And so we want to support more protocols, verify more properties, achieve a form of practical lightweight verification of concurrently distributed systems in Scala 3. But for that, there is more work to do, and your opinions are really helpful. So this is it. Thanks for your time.